We are all looking forward to seeing an actual math battle in action, myself included. And I'd like to briefly introduce this event, and I'd also like to hand out the problems that that each of the two groups of students have been working on for the last hour and a half behind the scenes. So let me get these started here. Oh, these seats are taken. It's not available. That's correct. Yeah. And we'll get these started here. So I would also encourage you to glance in your packet. If you haven't already seen them, there are rules of engagement that describe more or less how a math battle operates. And I think maybe I won't spend a lot of time now describing the rules. I'll let you glance at those as the event unfolds. You'll catch on pretty quickly. What I would like to do is introduce the judges, the esteemed judges for today's event. There are three of us. I'm Sam Vandervelde, and Ravi Vakil is joining us this afternoon. And a special guest actually is with us, Eugenia. And I'm not going to attempt to pronounce your last name. It's okay. Eugenia is a student from Russia who has participated in math battles in Russia as part of her high school experience. Is that fair? Well, so she is our only math battle veteran, I think, amongst the three of us. So let me ask at this point for our two captains to come forward. We're going to conduct the Captain's Challenge, which determines the order of play. So we have, and I'd like the captains to test out their microphones by introducing themselves.
Hi, I'm Evan O'Dorney.
Yeah. And our captain here, hastily elected.
I'm John Boyle.
So the way this event begins is I'm going to ask a simple yes/no question. And each of our captains is going to, when they feel they are confident enough about the answer, raise their hand. We'll identify the first hand that goes up. I'll call on you by name so you know which person I'm after. And they will immediately give a response. So are you ready?
Yeah.
For the question? I've written a number on the board behind me. The number is as follows. Is this number a perfect square? Evan?
Yes.
That is correct. Evan, would you mind telling us what it's the square of?
A number consisting of 9 ones in a row.
Ah, very good. That's correct. So, thank you, captains. You can sit down. Turn off your mic. Evan, you need to decide for us if your team is going to retain the right to challenge or if you want to pass that to the other team. Okay, your decision is before you choose that problem, do you want to challenge the other team or do you want to pass that to them? Fortunately, the outcome doesn't hinge on this decision. Okay, time's up. What's your decision?
We challenge them to present number 3.
Okay, they're going to challenge. Turn it off. And the challenge is problem number 3 to the opposing team. Do you accept the challenge or do you want to return it?
I accept it.
Okay, take it away. Yes, and 5 minutes.
Okay, so you all have number 3 in front of you. Shall I read it? Okay. Consider the collection of all 3 element subsets of 1, 2, 3, the integers up to n. Prove that there are as many subsets in which one of the elements equals the sum of the other 2, as there are subsets in which one of the elements is the average of the other 2. I'm going to prove this by induction. So we start with the base case of the set 1, 2, 3. The statement is obviously true for this subset because there is one subset in which, there's one subset total, and 3 is 1 plus 2, so that fits the adds. That fits the first property, and the second property, 2 is the average of the other 2 elements. So that's our base case. Now we go for the induction step. Now suppose that we have the set 1 up to n, and now we add the element n plus 1. We want to, so we're given that the number of subsets, 3-element subsets in which one element is the sum of the other 2, is equal to the number of 3-element subsets in which one element is the average of the other 2. We're given that that's true of this. Is it still true when we add n plus 1? So all of the new 3-element subsets will contain n plus 1 and 2 other elements. So how many new subsets fit the sum property? Also, if we write the numbers in decreasing order, the first number is, okay. The first number will be n plus, okay. The first number will be n plus 1. The next number will be some number a, and the third number will be n, okay. The next number down will be n plus 1, okay. N plus 1 minus a, and the last number will be a. So how many of these subsets are there? Well, so a can be any number from 1 up to about half of n plus 1. Specifically, if n plus 1 is even, then okay. So okay, if n is odd, then n plus 1 is even, and so there will be n plus 1 over 2. Okay. Yeah. Oh, okay. Let's see. Okay, these numbers have to be distinct and they're decreasing, so basically there will be floor of n over 2 of these new subsets. Because if n is odd, then n plus 1 over 2 is the number of these pairs, except in the last one, these two are the same number, so that's not a 3-element subset of it. So there are a floor of n over 2 of these new subsets, and then for the average property, it has to be n plus 1, n plus 1 minus d, n plus 1 minus 2d. And I say that there will again be floor of n over 2 of these.
Sahana should do it.
So at this point, it's sort of a mix of mathematics and debate. You're starting to realize. At this point, we invite one member of the other group to respond to the solution presented by John. They have choice. They can either try to elaborate on what he's presented, or fill in if they want, or offer an alternative solution. They only have 3 minutes to respond. And in doing so, they're attempting to score some of the available points for their group. There's 7 available points for this problem. So have you decided who's going to respond? Sahana, so come up, please, introduce yourself, and then you can respond to the question.
Sahana.
Here you go. Does that turn up?
Hello.
Very good. Go ahead and say your name one more time.
I'm Sahana. Okay.
Okay.
So another solution is you could consider the cases where n is odd and n is even separately. And you can compute the number of subsets such that one of the elements is the average of the other two, and one of the elements is the sum of the other two for each of these cases. So for this one, let x, y, and z be the elements, and without loss of generality, you can just assume that x is equal to y plus z to compute the number of subsets such that one element is the sum of the other two. So if x is equal to 1, there's no solution. And if x is equal to 2, there's also no solutions for y and z. And if x is equal to 3, there's one solution, which is 1 and 2. If x is equal to 4, there's one solution, and so on until and so until if x is equal to okay, so and so until this, which only repeats one time, and if x is the average of y and z, which means that 2x is equal to y plus z, then if you do the computation, you get the number that's equal to this. And similarly, if x is even, and x is equal to y plus z, okay, you get something equal to this, so that proves it.
At this point, the judges traditionally can either offer remarks or otherwise ask questions about, if just to clarify either the solutions. Do we as the judges have any other questions or remarks to add? Well, then we'll pause for a minute and assign scores for the first round. In the meantime, our other team now has a choice of which problem to challenge the group on the left to. So I'll let you think about that while we deliberate. Would like to announce our first score, and that is we're awarding 6 points to our first presentation and a point for the response from the Berkeley team. So thank you again, both students, and let's turn it over to our Stanford group. What's your decision? They're challenging the Berkeley group to number 7. Do you want to accept the challenge or return it?
We want to return it.
They have chosen to return it. I should explain that at this point, the problem becomes worth 10 points instead of just 7, so as to provide some incentive, of course, for this group to take it on, even if they don't have a complete solution. They're banking on the fact that our original team doesn't have a solution. So you are on board to solve number 7, and you can choose which person is going to present it. Okay, please welcome Brian.
Okay, so we're given a quadrilateral ABCD that's cyclic. So we'll draw that circle. And then we're given that if M and N are the midpoints of A, B, and CD, and if segment MN is drawn. Let's see. Like this, and if O is the centrum, so then we pick a point P here, such that AM equals to MB equals to DN, so, and MD equals to MP equals to dn equals to cn, like this. So what this tells us, first of all, is that mn equals to 1/2 of AB plus CD, because AM is 1/2 of AB, and then DN is 1/2 of CD, and these translate to these two lengths. So that gives us that condition. And then now, if instead of picking point P here, such that MP equals to DN and PN equals to AM, if instead we pick the point such that, so let's pick a point here, let's call it Q, such that MQ equals to AM and QN equals to DN. And we know we can do that because still we will have MQ plus QN equals to 1/2 AB plus CD. So we know that we can pick Q like that. Then we see that since the median to the then we see that triangle AQB must be a right triangle. So we can draw a circle we can draw a circle ABQ, which will have M as its center. And then we can also draw a circle DCQ, which will have N as its center. The reason we can do that is because if we have AM equals to QM, then we have that the angle MAQ equals to MQA. And if MQ equals to MB, then the angle MQB equals to MBQ. And because the angle AQB is therefore half of the sum of the angles in the triangle, which is 90 degrees. And so we know that this AQB forms a right triangle. So we can draw that circle. And now we see that since MQ and N lie on a line, therefore the circles with centers M and N are tangent to each other at Q. And also, if we add the midpoint of MN, let's call it R. Then we see that R is also the midpoint of QP because we have MP equals to DN and NQ equals to DN. And NR is equal to 1/4. Okay. And NR is equal to 1/4 of AB plus CD. Because we defined R to be the midpoint of NM, and MN is that length. So then we see that P... We see that PR equals to let's see. PR equals to MP minus MR equals to DN minus N, wait. Yeah. So R is the midpoint of PQ.
So now we'll invite the Berkeley group to nominate one person to respond to. So which person would you like to come up? Go for the partial credit. You can do it. All right. So please welcome, this is Spencer?
It's Aaron.
Aaron. Thank you. Please welcome Aaron.
Um, so I figured out that wait, this is point M, this is point N, and then well, this O right here. So this is equal to that because this is the midpoint N, and similarly this is the midpoint, so that's equal to that. Oh, so OM is equal to OM, and ON is equal to ON, and also OA, OB, OC, and OD are all equal because they're all radii of the circle. So therefore, this triangle is similar. I mean, it's congruent to this triangle by SSS, and this is also congruent to that. And I also found that squares, this can't be a square or a rectangle, otherwise O will be on P. And trapezoid won't work because it will have to be an isosceles trapezoid for it to be cyclic. So if this was M and this was N, then O would lie on MN, so that wouldn't work. But if this was M and this was N, then O would still lie on MN, and that wouldn't work either.
So just as before, we need to decide. Yeah, so at this point, let me just clarify that our Stanford group made a challenge which was returned, and so the first task will be to decide if they made sufficient progress on the problem. If so, then the right to challenge passes back and forth. And if not, then they have to challenge again to give the group on the right an opportunity to solve a problem. So part of the scoring, that's what is happening with part of the scoring. So we'll be right back. So the judges would actually like to call Brian back to the board to basically to ask him how to complete, sort of how to take the idea so far and just sort of in general how they might lead towards a solution.
One possibility is to invert about a circle with center Q. One possibility is to invert about a circle with center Q, because we see that we have circles AQB, DQC, and ABCD. So that's one possibility. Another possibility is, since R is the midpoint of QP, if we pick we have to show that OPQ is a right, or angle OP is perpendicular to MN. So let's see. Okay, if we pick the midpoint of OQ, right there, we can show that these three lengths. So let's call this C, or we could call it F. We could show QF equals to FP equals to FO.
Okay, so the judges would like to award 2 points to the Stanford team, 1 point to the Berkeley team, and 7 points to themselves. That's how it works. They're right. I didn't make up the rules. And what that means is that the Stanford team holds on to the right to challenge. So once again, you're going to choose a question to challenge the other team with. So at this point, you can decide which one that will be. Okay, so have you decided?
Okay, number 2.
They're challenging you to number 2. Do you accept the challenge? Okay. And again, could you introduce yourself as part of your solution? And I'm going to give you some more board space.
My name is Feng Ning. So let's suppose Mn Mn plus 1 and all the way to Mn plus Am plus k. Suppose this is a subsequence of the original sequence. and such that they are all consecutive positive integers. Okay, so then the definition of this sequence gives us am plus 1 equals am plus am plus 3. And also gives us am plus 2 equals am plus 1 plus am plus 4. And since am plus 1 is given here, this thing equals am plus 3 plus am plus 4. And so therefore, the number am plus 3 equals am plus 2 plus am plus 5. And so we solve for this variable, and we get and we substitute this expression into this, and this thing will give us, we notice that am plus 3's cancel out, so we get negative am plus 4. And since our original assumption is that they are all positive, this thing is definitely less than 0. So therefore, like you can only have 5 members in the sequence: am plus 1, am plus 2, am plus 3, am plus 4, and that satisfy the criteria because am plus 5 would then have to be negative. And so then all that remains is to construct such a sequence. And so then you can choose the sequence to equal 1, 2, 3, 1, 1, which gives us 1 plus 1 equals 2, and 2 plus 1 equals 3. And this shows us an example of A that has like 5 consecutive positive integers. And this proves that you need there is at most 5 consecutive positive integers. And so therefore the sequence has at most 5 positive integers, which will solve the problem.
So now we'll invite a member of the group on the left to respond. And let me take just a minute to say that in a response, you do have a lot of options. You can either try to clarify a point in the other solution. You can try to give a completely different solution, but the time is deliberately shorter to encourage you to respond to the original solution. And only if you have a really snappy, something that can fit in 3 minutes, then you can bring that into the bring that up as well. So I'll let this group choose a person to respond now. By the way, the idea is for each person to be at the board once in the course of the afternoon. So their choices on who comes up continually gets whittled down as the day goes on. Yeah.
A responder can come up to present, right?
No, a responder is one of. There are only 6 problems that get discussed in the course of the event. So one person from each team presents something and one person responds. So that's one of each of the 6. Does that make sense?
Oh, we had gotten that the solution was a maximum of 3, although that serves as a counterexample. Yeah. So, yeah, we figured that. We were operating under a different set of assumptions that we think the problem was a bit unclear because this was assuming that it meant numbers that are all consecutive to a different number in the sequence. We were assuming that it had to be either increasing consecutive or decreasing consecutive, in which case it would be 3. And the proof that 3 works is that if you just have the first 3 numbers being 1, 2, and 3, and you can't then you haven't gotten the n plus 3 term in there yet, so that works. And if you have a1, a2, a3, and a4, such that a2 is a1 plus 1, a3 is a2 plus 1, and a4 is a3 plus 1, it does not work because you must have a1 plus a4 equals a2, and you have that a2 equals a1 plus 1, and a4 equals a1 plus 3. What? Okay. And then you have that 2a1 plus 3 equals a1 plus 1 just by substituting into this. So then you subtract a1 from both sides, and then you subtract 1 from both sides, and you get a1 equals -2, which is not allowed. So if you assume that it has to be increasing, then you get that it can only be 3. And even if you assume that it can be decreasing, you can do the same thing backwards, where a1 plus 1 equals a2, etc. And you get that a4 must be -1. So you can't get a sequence of 4 with that either.
So the judges have decided to award 6 points for the initial solution, which was basically complete, but we felt that the second team did add something substantially to the discussion, so we'd like to give them one of the points. So we decided on a 6-1 split, and I believe now the right to challenge has passed to the Berkeley group. What problem would you like to challenge at this point?
Number 8.
I challenge you to solve number 8. Do you accept the challenge, or would you like to return it? I accept the challenge. Okay, and Timothy, you'll be presenting? Please welcome Timothy.
Okay, so the problem asks for in an oh yeah, Drew draws some diagonals within the unit squares of an 8x8 chessboard so that none of the diagonals intersect even at their endpoints. So we can draw an 8x8 chessboard here. Anyway, so here we have an 8x8 chessboard, and they want you to connect the diagonals of the square so that like none of the diagonals except even at their endpoint. So they asked to find with proof the maximum numbers of diagonals that Drew can draw. So we're going to claim that the number is actually 36 because you can do it like this. Oops, nothing's here. Wait, I screwed up somewhere. Oh, okay. All right, so this gives us a 36 point we desire. So the question is like find it with proof. So obviously the number is going to be less than 40 because you have 81 points and each square uses 2 of the points, and like each point is only used once. So you definitively have an upper bound of 40, but we're going to actually try and inductively prove that the answer is going to be like the sum of these odd numbers, whatever they actually come to. So, can I move this up? So we're going to do this by considering inducting on by 2s, basically, so that when you jump from like 6 to 8, you're going to add 15 to it, and in general, you're going to add, when you jump from 2n to 2n plus 2, you're going to add 4n plus 3. Is that right? That's wrong. Close enough. But anyways, whatever gives you 15 in the end here. But so when we induct, we basically add, this is like our original square. We've got a bunch of points here. And then you've got points here. So that this is n. And this is n plus 2. Whatever. So you've got a whole bunch of points here. So basically, you know that if you look at these points exclusively, you know that each basically diagonal inside your new square must pass through one of these points on here. And there just so happen to be like 4n plus 3 of them, I think, that comes out to. But however many points there are on here, that completes our inductive step. But the only problem that we actually run into here is that this all works fine and dandy until you come to this point. And then you're like, oh darn. So if you come to this point, you basically know that for anything to go to this point, you must have it slanted this way. So now we get it split into 2 cases. The first case is that all the diagonals look like this, and they go downward this way when this is the corner on this new split field, that is. So that's our first case, that all the diagonals are down this way. And the second case is that we have one diagonal down this way, and somewhere down the road we have a diagonal going up this way. So the way we're going to deal with case number 2. We can deal with case number 2 because if you have a diagonal going down one way, at a certain point here, you must have a diagonal going up because each of these points must be covered. If one of these points is not covered, then our inductive step is already complete because we've only added one extra diagonal, and then if one of these points is not covered, we've taken out one of the diagonals. So clearly you must have an arrangement that looks like this, where these are on the lattice of a 2 by 2. So when you look at this, each of these are on the lattice of a 2 by 2. So after this point, you know that none of these two can be covered. So then you'd have to, your following things would all be like flying upwards, kind of. But anyways, in the end, you would get that at the corner point, you would have to have, at the edge points, you would have to have a diagonal basically going through here, so that you'd be able to cover this point nicely. And then at the other opposing place, you must have a diagonal covering here. So it either looks like this or this. And the point covering here either looks like this or this. Well, where was I going with this? Okay, anyways, if you had a point looking like this, we're going to claim that you can't have a point looking like this, because if in our inductive step, we're going to add the claim that one of these 2 squares must these 2 squares on the corner here, we're going to claim, must be filled in so that this diagonal can't be placed. So if this does indeed.
So we invite a member of the Berkeley team to respond, and you can just find a blank board. I think if you lift that one.
Hi, my name is William from Vandervelde and Pleasanton. I'm representing the Berkeley team. I didn't really understand what Tim was trying to say, so I'll try to make things more intuitive and easier to understand right now. So my proof comes in 2 steps. The first step is to prove that 36 works, and thankfully Tim has already done that for me, thankfully. And then the second step is to prove that you can't do more than 36. If I prove both of those, then I can show that 36 is the maximum amount of diagonals that Drew, not Tim, can place, that Drew can place on a checkerboard. So let's see. Let's see some properties of these diagonals right here. We see that each diagonal can only, there's two different kinds of vertices on this checkerboard. These are the even vertices, and the ones that are not circled are the odd vertices. We see that each diagonal only covers, either two even vertices or 2 odd vertices. So right here, we can even distinguish these vertices even more. Vertices that are very even, like right here, these are A vertices. We can distinguish vertices that are odd even. These are distinguished by B right here. That every diagonal that covers a point in A must touch a point, must touch B. So the limiting factor here is B. The amount of B's is the maximum amount of diagonals, covering even vertices you can have. So we can see here there are 16. There are 16 B vertices. Therefore, the maximum amount of A vertices you can use is 16. So 25, the amount of A vertices minus 16. So that means 9 A vertices are left unused. So let's go back. There are 81 vertices in total. 9 are unusable. 72 vertices are usable. If we divide that by 2, finding the amount of diagonals, we see that there are 36 diagonals that can use usable vertices. Now we can't have more than 36 diagonals, because if we had more than 36 diagonals, we would be using unusable vertices. So right here we have shown that Drew can fill the board with 36 diagonals, and Drew cannot fill the board with more than 36 diagonals. So therefore, the maximum amount of diagonals that Drew can put on a chessboard is 36. Thank you.
So the esteemed panel of judges has decided to award 3 points to the Stanford team and the remaining 4 points to the Berkeley team. Well done. Let's see. This is the hardest part of the whole event. Whose turn is it to challenge who? I have completely forgotten where we're here. So Stanford is challenging the Berkeley group. Us to do. Yeah, that's right. Challenge. And then that was the response. Yes, so it's the Stanford team. Yeah, like a big arrow just to turn one way and the other way. Yes, in fact, we should. All right, so this team will choose a problem to challenge.
Six.
The challenge for problem 6 has been made. Will they accept the challenge or return it? Okay, they've chosen to accept the challenge. The first part of the challenge is to erase the board on the right. Take it away, Evan, and I will work on the board on the left.
All right, we have this equation. F of x plus y is equal to f of x plus f of y plus 80xy. So here's the trick that I'm going to use. I'm going to say f of x is equal to 40x squared plus g of x. So g of x is a function defined by g of x equals f of x minus 40x squared. And now I'm going to substitute this equation into this one. So we have 40 times x plus y squared plus g of x plus y is equal to 40x squared plus g of x plus 40y squared plus g of y plus 80xy. And if you expand out the value of this term, you can see that it exactly cancels with this term, and this term. And we get g of x plus y is equal to g of x plus g of y. And this is a very famous functional equation. And its solutions are given by g of x is equal to g of 1 times x whenever x is a rational number. It could have other values over the real numbers, but we don't care about them. We know that this equation always holds true when x is a rational number. So what we're going to do is we're given that g of 1/4 is equal to 2. Is this correct? And so f of 1/4 is equal to 2. So that's equal to 40 times 1/4 squared plus g of 1/4, which is g of 1 times 1/4, is equal to 2. And so we can solve this equation. And these cancel. This cancels. We get 5/2. We move that to the other side. We get negative 1/2 is equal to g of 1 times 1/4. And so g of 1 multiplying both sides by 4 is negative 2. And now we want f of 4/5, so first we find g of 4/5. And that's going to equal g of 1 times 4/5, which is going to equal negative 8/5. Finally, we calculate f of 4/5. It's equal to 40 times 4/5 squared plus g of 4/5, which is minus 8/5. And now this cancels, we get an 8. And so 4 times 4 is 16, times 8 is 128. 128 minus 8 over 5, which is 120 over 5, which is 24. So therefore, f of 4/5 is equal to 24.
Okay, I'm going to present two different solutions to this problem, and they're not, one of them is a lot of algebra, so I'm just going to skip to the most important parts of the problem. So first of all, we know that f of 0 is equal to 0 because you could just plug in f of 0 plus 0 into the problem, and then that will get us f of 0 equals 0. And then from there, we can also get that f of x minus x equals f of x plus f of negative x minus 80x squared. And then from there, we can get that. And then since this is f of 0 right here, so we get that f of x plus f of negative x equals 80x squared. And then we can do that f of 1 minus 1/5 equals equals f of 4/5, which is also the same as doing f of 1/5 plus 1/5 plus 1/5 plus 1/5. And then from there we can get that. I'm going to skip a lot of algebra that involves like plugging in that solution. So we get that. We have 22 plus f of negative 1/5. That's what you get from doing this part. And equals 4f of 1/5 plus 96 over 5. Oh, and you can get f of 1 by just doing f of 1/4 plus 1/4, which is 1/2, and then 1/2 plus 1/2, which is 1. And then from there, you can also use this equation to get that f of 1/5 plus f of negative 1/5 equals 16 over 5. And then you can solve for f1 and f of negative 1/5, which you get as these solutions. And then you plug that into f of 4/5, and then you get 24. And then the other way you could also do it is by doing induction. And from there you can use the fact that you can get the formula. And then from there you can plug in x as 4, and then no. All right.
I think you've got my problem set.
Oh, I do? Sorry.
Thank you.
Yep.
So we'd like to award 6 points for the first solution and 1 point for the additional approach presented by the response. And that brings us to, I think, our final question of the day. Now, there are 9 problems altogether that we let all of the students work on. The idea is that this affords some flexibility in terms of what problems they like to choose to work on up here. So there are 4 problems left to choose from, and I believe the arrow is pointing this way. So, which problem would you like to challenge?
Number 9.
They've challenged number 9. It sounds like they'll accept the challenge. And please welcome Austin.
No? Still? Hello? Okay. So problem 9 was find solutions to this equation that you see on the paper. And this is one of those problems where you try to look for an elegant solution before you figure out that brute forcing is faster. Yeah, so right, so then I multiplied so we assumed without loss of generality that the 3 numbers x and y and z sum to 1. Because if they don't, we can divide by anything we want afterwards. Yeah. And then we substitute this in. And then we do a lot of algebra. And if I had to write out all the equations, it would probably go on for a lot longer than 5 minutes. But you like combine all the fractions into one. So it becomes so I'm not going to write everything like so when you expand everything, stuff cancels. And I'm running out of space. Okay. You end up getting this complicated thing over the denominator, but the denominator is like irrelevant because we only need to look at the numerator to find solutions. And then this ends up factoring as and so we see that in order for this to be 0, 2 of the
out of x, y, and z, at least two have to be equal.
For number 9, we assume x does not equal. So if any two are equal, it's easy to check the expression equals 0. So and we multiply out by y plus 0 and z plus x. And we have z is a cubic, so so in order to get rid of z as a cubic, we have to set it equal to one of a function of x and y to set all three equal to make it equal to 0. So it has three roots: z equals x, z equals y, and z equals negative x minus y. So will equal 0. And z equals negative x minus y doesn't work because then either z or x plus y will have to be 0. Will have to be negative, and that's not allowed. Therefore, at least two of them have to be equal.
So we have after lengthy deliberation. This was a tough one. We decided to award 5 points to the original presentation and 2 points to the response for the alternate approach. And that brings us to the end of the day, and I have to say that, so first of all, I'd like to say that I was really impressed with your progress. I put together the problems, and you may be curious to know where they came from. The set of problems consists largely of problems taken from an actual Russian problem set that we obtained while we were visiting Moscow a couple of years ago as part of the MSRI trip, and those were slightly translated and put into the format that you had today. But you were largely working on those set of problems, and I had no idea whether there would be just too easy or too hard. And anyway, I hope you enjoyed working on them. I'd also like to say that we have awards today for the winners, and you're looking at them, all 12 of them. So please give them a big round of applause. So what we've put together for you is a copy of Peter Winkler's new collection of mathematical puzzles, which is a delightful little collection called Mind Benders, and tucked inside each of them is a $10 gift certificate to Cold Stone Creamery when you need a break from working on the math. So we'll have one of these for each of you. We also have final numbers, and that is...
So in third place, with 9 points, was the judging panel. In second place with 18 points was the Stanford team. And in first place with 20 points was the Berkeley team.
Very close. Well done, guys. Very good. So please come and congratulate all the participants. I have copies of solutions to all of the problems, which I've been guarding fiercely, but I'll set those out on the back table perhaps. And
before we move anywhere, I have an announcement.
good. I was about to. Why don't we just do an announcement?
All right.